Yeah, thank you all for coming. I know this has been a long week, and this is certainly the last event in this center. You've probably been to many events, so I hope this one's interesting for you. What I really want to do is lay out how NASA is able to use models alongside the substantial suite of observations that we have to try to tease out from these observations more than we can get from any one instrument in particular. So the basic idea of Earth system modeling and data analysis is to try to combine information from multiple sources and understand much more about the Earth system. And then I want to show you how we've used that in certain applications, and in particular, a thing that NASA has been very central to in the United States is the ozone monitoring and the Montreal Protocol. What we do in our office is very strongly linked to combining meteorological features with air quality. I'm going to show you some aerosols and other aspects of air quality in the Earth system. And then I'm going to finish up with some thoughts about the carbon cycle, where we are right now, how we can measure things, and how we might be able to push forward and use the models and observations together with the right type of investments and the right type of collaborations with other agencies to try to understand things better than we do already and potentially even monitor that into the future. And I've tried to just highlight on this first slide a few of the different types of observations that NASA has, whether it's ice or whether it's land and sediments around the oceans, phytoplanktons, maps of precipitation, snow cover over North America with frozen lakes, tropical cyclones, and river sediments. We can measure so many different components now of the Earth system from space that it's really remarkable how just a couple of decades or a few decades ago we were putting the first rockets in space and making measurements, and the amount of detail we're able to get these days is really phenomenal, I think, from an aesthetic perspective. But there's also just so much scientific development has been based on these observations that and that's what I want to try to emphasize. That didn't go. This is the fleet of satellite that NASA is currently operating. I think there are 17 platforms in space. Most of these are orbiting around the poles, so they essentially go around the Earth in a circle, and the Earth spins underneath them. And with that type of geometry, we essentially see the whole surface of the Earth every day from these instruments. Some of them are measuring reflected sunlight, so we only see it on the day side. And there's just a couple of exceptions to that type of orbit. We're involved with the Discover mission, which is primarily led by NOAA, but NASA has instrumentation on it. That's basically sitting 1 million miles away from Earth and looking always at the day side of Earth. It's between the Earth and the sun, so you can always see the daytime side of Earth. And that's going to give us a lot of information about clouds, aerosols, and ozone as the algorithms for using those data become mature. It's only been up there for about a year. And the other thing that we have that's very unique to NASA is the access to the International Space Station. We're obviously a partner in that. And we've got several instruments on that already. RapidScat, for instance, is measuring winds over the ocean surface. We're able to use those to help improve weather forecasting, as well as monitor transport of things. And CATS, this one here, CATS is an aerosol measurement mission. It's an experimental type of technique for measuring aerosols. And that's another factor that is unique about NASA. We really do experimental types of missions. We're always pushing the frontiers of technology to put up new ways of observing things. Things that eventually may transition to a more operational phase, and then they're possibly going to be run in the US by NOAA. And I think there's parallels to that type of operation in Europe, too, with the roles of the different meteorological and space agencies combining. That's one of the strengths of NASA. We're not looking in general for operational type missions. We're really looking at missions that initially would have a lifetime of a few years. Often we do much better than that. Something's put up with a 3-year mission duration, and TRIM, for instance, I think had a 3-year lifetime. It ran for 17 years or something like that. So, but that's our initial goals, and then they become useful for climate monitoring as well. So, as I say, a very wide range of instruments is available to NASA, and that's really the heart of all of the work that we do. Moving on. So what I want to do now is just show a few examples of how information from a single observing system can inform society. And there are 4 examples I'm going to show: the width of rivers in North America, global maps of cloud cover, mapping global fields of precipitation using GPM, and monitoring changes in the Greenland ice sheet. These are all different parts of the Earth system, And I just want to show a few of these as examples of how one observation type can be used in isolation to illustrate these facts. This is an analysis that was published, and it's based on Landsat data, and it's a very detailed analysis done at the University of North Carolina. A very important part of the hydrological cycle over North America is the flow of the country in rivers. You get basically evaporation, precipitation, and some moisture stays in the soils, and then the rivers flow off. And this is really showing us that from using space-based data, we can come up with fairly detailed maps of the widths of rivers, and that's going to enable us to account more for the flow of water off the country, and monitor the total hydrological cycle combined with information about precipitation from other platforms. Also, in terms of Earth system science, nutrients get into rivers, they flow out, and with river flow, they flow into the oceans. So this helps us contribute to that type of information as well. That's example one. The second example, this is an animation, and this is the cloud fraction from MODIS. Now, typically clouds would have been measured, from an in situ measurement. Over time, we've got more and more satellites. MODIS is giving us very fine information about the spatial structure of clouds all over the globe as it orbits around. And these are monthly cloud fractions going through a year or so. And you can essentially see the shifting clouds with the seasons. You can see the dense cloud over the maritime continent here, and typical tropical cloud belts, the intertropical convergence zone. You can see the dry areas over the Sahara Desert there, over the deserts, and also the subtropical dry zones here where there's very little cloud compared to other regions. Again, another component of the climate system. Cloud fraction, of course, is related to the amount of precipitation you're getting anywhere. Clouds also reflect the solar energy back. That's, in fact, what we're observing with this. And so that's contributing to the total radiation balance of Earth. Sun coming in, part of it being reflected back, part of it being absorbed in the atmosphere and at the Earth's surface. So lots of information about clouds from MODIS here. Another part of the hydrological cycle, global precipitation measurement mission. So I mentioned TRIM already. That was launched in 1997 and functioned for about 17 years. In 2014, the successor instrument, it's a collaboration with the Japanese Space Agency, and this is the Global Precipitation Mission, and this is merged precipitation data produced at NASA Goddard, and it's showing the intensity of precipitation. So the dark reds here are very intense storms, a lot of precipitation coming down. So you can see, again, over this region, the Indonesian region, the Western Pacific, the intense rainfall, the rain bands extending all the way across the Pacific, across the Atlantic as well. Sort of more stationary patterns, bubbling convection type things localized in the tropics, whereas at the higher latitudes, you're seeing the weather systems move through more sort of long stretched, organized bands of rain. And those are the frontal systems that bring us weather. In terms of contributing to climate, the record of TRIM plus GPM, as that extends into the future, is going to give us a much more detailed maps of precipitation for monitoring that than we've ever had before, because typically we can't measure this over oceans because most of our in situ observing systems are land-based. And this differs from other types of satellite measurements because it really is measuring things that tell us directly about the precipitation in the clouds, not about the cloud, just the existence of clouds, which is what we typically be able to infer from other observing systems. And here's the fourth example. This is GRACE. GRACE is a very interesting observing system. It's a pair of satellites, and their orbits are controlled somewhat by the variations in the mass at the surface of the Earth. And what that does, it pulls them preferentially. So when they get closer together, if there's an extra large mass at the surface of the Earth, they get a little closer together. If there's less mass, they move slightly further apart. And we can measure this very precisely. And that separation then can be used to infer about the mass of the surface of the Earth. So as they pass over Greenland, we can infer how much mass is on the Greenland ice sheet. And essentially, this has been flying for about a decade or so. And as time has gone by, the mass has decreased from about 0 to about, we've lost about 2,500 gigatons of equivalent water from the Greenland ice sheet. So this is, again, an example of a single satellite demonstrating very clearly that Greenland is losing mass. This is ice turning to water, which is going into the oceans and causing sea level rise. Also, it's also a a source of fresh water for the oceans as well, reducing the salinity in those regions. So again, and you can see as well that most of that mass loss is from around the edge of the continent, which is probably what we expect, where it melts faster and flows off. So that was just a few examples of the different types of features that we can measure from space, and I've tried to put those into the context of how they can be used for climate purposes. What I'd like to come into now is a little bit about using models to connect Earth system observations together. Essentially, I've shown you can use observations from one satellite to understand something, but imagine how powerful it is when you can use some very intelligent, very sophisticated model and very complex computing resources to pull all of the information from different platforms together and try to understand, come up with a more complete picture of the processes at work. So how the precipitation from TRMM affects the moisture on the soils, and we can actually measure that now with SMAP, for instance. And so we can come up with balances between how much it's raining, how much water remains in the soil, and we can also start relating that to the greenness of the vegetation that we can see from space. So we can come up with complete pictures of both the hydrological cycle and the effects on vegetation, and hence the effects on the carbon cycle, because it's the vegetation that is doing the photosynthesis that takes the carbon out of the atmosphere. So I want to just try to give a few examples of how we use models at NASA. The first type of models that have been widely used are diagnostic models, and they basically don't have a time component. You basically say, we have this, and we get that, and it's a kind of a causal relationship. And they're very, very useful for understanding processes and tying satellite data together at the initial stage. But what we really need to do as a community is to start looking at how the system evolves, and the time dimension is very important to this. And that's why we need sort of models with a predictive capability here. Basically, we're going to say, going forward, and as we do this exactly for weather, for instance, we take in measurements of temperature and winds and humidity, and we bring this all together by a process called data assimilation, which is basically a sophisticated statistical technique to combine these things. And we then make a forecast out to about 10 days, and that tells us what's the weather going to do, tomorrow, the day after that. And everyone knows that over the past decade or so, as the computing resources have become much more available, and as the models have increased in complexity, the quality of our forecasts has improved, and that's the aspect of prediction that affects us most in our day-to-day lives. What we're really trying to do with the Earth system models is try to bring up a predictive capacity for the whole Earth system, the weather, the climate, as you will, what's going on in the land surface, the state of the oceans, the state of the ice sheets, and the state of the carbon cycle in that context. And as we're able to develop these models and make them more complex, and as our computing resources grow to be able to do that, we should be able to make more, better predictions. And really, a key part of that is having good observations to initialize them with. And that's what we've seen with weather. As we've got more and more satellites up, giving us more and more information, the strength of the initial condition is greater. We're able to make better forecasts. And that's essentially what we would like to do for climate forecasting as well, coupled with carbon. So I just want to show a couple of examples here. The first one is predictions of ice on seasonal timescales, and the second one is aerosols and chemistry, and that's very related to air quality going into the health domain. So the first one, this is just a static image, and it's essentially showing the prediction of Arctic sea ice in September of 2014 from a version of our GEOS5 model that was initialized in May of 2014. And this is the prediction here. You can see basically, dense ice in the center of this ice sheet. Here's Greenland, but then there's no ice around the entire the ocean area north of Siberia and Canada. And in terms of the observation, you can see a similar ice extent. There's obviously a lot of details that are not correct in this image, but the metric for this type of prediction at present is more or less the area covered by ice. And we were actually, of all of the models around the world that actually make these predictions, this was actually the most successful forecast there was in 2014. on the 5-month timescale. That's not to say that the same would have been true of 2013. I think we're going to need a good few years before we can start assessing relative skills of models. But the point being, there is skill in this forecast right now based on initialization with information about ice, information about the oceans, the atmosphere, and the land in our system. And a lot of that in our models does come from NASA observations in conjunction with the operational fleets from NOAA and the Europeans and the Japanese and everyone. And the second example was not what I expected to see. Let's see what's next. Oh, aerosol. Okay, let me get to the aerosols first. Yeah, sorry. This is actually a model simulation, and it's showing different types of aerosols in the atmosphere. This is a fairly widely known movie at this point. The point being, this is a model simulation. It's showing sea salt in blue. It's showing carbonaceous aerosol from burning, from fires in green. It's showing dust in orange, and it's showing sulfate aerosols in white. And just going through these different types of aerosols, sea salt is pretty much a natural source. It's by wind flowing over the ocean. It picks up the salt, and then it gets lofted, and it's transported for fairly long distances. Aerosol will typically stay in the atmosphere for periods of about 10 days. And so you can actually see the long-range transport of that here. Fires, in this model, even though the actual aerosol is not constrained by any observations, the sources of these aerosols are constrained by observations of hotspots on the Earth's surface that we get from the MODIS satellite. So even though this isn't a real atmosphere running here, it does have realistic sources of fire. And the fires here are related to tropical forest burning and also agricultural practices in Africa and Brazil. And you can see those everywhere. Boreal forests burning in Siberia here, in this case. The dust is, again, a natural process flowing over the desert, picks up dust, lofts it, and it takes it. And you can see very clearly how it's able to transport Saharan dust all the way to the Caribbean islands, to Central America, and occasionally to North America and South America as well. And the other aspect to this, the sulfate aerosols, this is almost entirely caused by burning. It's an emission from power plants, from cars and things. And you can see the hotspots of sulfate aerosol emissions in white are Asia, Europe, and especially the east coast of North America. And LA occasionally shows up as a strong source there. This is the anthropogenic pollution that's very prevalent. And you can see how a local emission very concentrated in certain regions, local emissions get picked up and transported very long distances into other countries and other continents even, affecting the air pollution there. So air quality for the people who live in those other continents is affected by emissions in different continents. This is really an example of how information from satellite data, even when combined with just a simulated atmosphere, can inform us about the long-range transport of aerosols, about the complexity of the mixing processes in the atmosphere. You can see them all being mixed up at various places into mixtures with each other, and affects how we think about air quality as being a non-local problem. And that's important. And that's not to downplay the importance of monitoring local emissions, because obviously local emissions have a local effect as well. And that's actually on the slide that I just skipped over. This is another pollutant that's emitted by combustion, essentially. NO2, nitrogen dioxide. This is a strong pollutant. It's very short-lived, so you see it pretty much in the regions where it's emitted. And this is a movie showing the cycle through the year of those emissions as they're measured from NASA's OMI satellite. Essentially, the hotspots are the large population centers where people drive a lot, where there's burning going on. NO2 is very important as a pollutant for air quality because it reacts and leads to the formation of ozone. Again, that's a health hazard for many people, especially asthmatics. And the importance of this one is that we're able to monitor from space the impacts of regulations that the EPA imposed in the mid-2000s. So each of these is a pair of images for 2005 to 2007 and for 2009 to 2011. And in many of these cities that we see, for instance, Tampa here, you can see a decrease in the amount of NO2 emissions between those two periods. And I won't go through them all, but you can, apart from LA, I think probably where there's a big basin containing everything, so it's hard to have much effect. There is a fairly substantial impact. It's actually shown continentally on this map here. So it's really showing how, first of all, the effects of emissions do affect the local air quality, and how we can monitor that from space, and showing what a powerful tool satellite observations are for such problems. I'll skip the aerosol movie since we've already seen it. The next, oh, thank you. The next thing I wanted to talk about was ozone depletion, and basically how scientists were able to demonstrate a problem with the use of CFCs. CFCs were used in the early 70s and that in hairspray and as refrigerants. And basically, some now Nobel Prize winning scientists demonstrated that these had harmful impacts on the ozone layer. The international community began to act, and things were sort of already in progress, but then the ozone hole appeared. And this was something that was just way off range. No one expected that. We'd expected some modest ozone depletion over the entire globe, but no one had thought that there was a particular chemical process happening on the surface of tiny little aerosol particles in the cold polar vortex that sits over over Antarctica at that time of year. The severity of ozone depletion in the ozone hole probably was one of the spurs to really push the international community to work together. They introduced the Montreal Protocol, which basically limited and phased out CFC production over time. And this is essentially working. The countries that signed it, the major producers of CFCs did adhere to it. And in the 2014 ozone assessment, I was lucky enough to be a co-author of that one. It was the first time we were really able to show that there has been an impact on ozone. And I want to spend a couple of slides showing that here. And just as an aside, though, NASA is mandated to produce the satellite observations to help monitor the ozone. And it's I think, the one piece of NASA's mandate that actually has the word monitoring in it, which is an important thing for us in some ways. This is an example of the ozone hole. Essentially, as time's gone by, in about 1960, we had ozone values around 350 Dobson units. That's basically if you squish all the ozone together in the atmosphere and put it to the surface, it's about, I think, 3.5 millimeters thick, or something like that, and that's what 350 Dobson units means. Over time, as we started using CFCs, depletion occurred. Around here, we started realizing the severity of the problem, and that led to the Montreal Protocol. And essentially, as the CFCs were phased out, you can see the ozone levels started to level off, and now they're projected to increase into the future. Note how quickly they decreased from that value down to about 150, so almost 2/3 at least of the ozone is gone in this region of the atmosphere in this season. Yeah, it's not all of the ozone from the atmosphere, but a very strong increase over about 20 years happened here. Note the recovery is going to take about 100 years, and that's just because once the CFCs get into the stratosphere, they are stuck. It's a very, very slow process. They're catalytic, so what they act once, they react again once they're restored. So it's not like react once and go away. It's really continuous. And that's a very important part of this, and also their lifetime up there, just because they recirculate. Eventually, they'll get back into the troposphere and get washed out. So this is essentially what we expect. We're at about this point now in that curve, and you can see some hint of an increase of ozone on this map. But these are obviously model projections because they're going into the future. And this is a comparison of what's actually happening, what we expect to do now, and what we've avoided by phasing out these CFCs. It's showing ozone concentrations in the stratosphere as a function of the chlorine concentrations. And now, as with the depletion, you can see the chlorine amount is being reduced over time. As without any Montreal Protocol, CFCs will continue to increase with time, and you can see a massive ozone hole developing. And I think as time goes by, this is going to extend further and further into the middle latitudes, and that means it's going to become more and more threatening to people. So this is what would have happened if the international community had not worked together to restrict CFC emissions. And I think that's setting a great precedent for us. There you go. You see, ozone is totally disappearing over the entire globe as we get into really high chlorine concentrations, which would happen by 2065. So by the middle of the 21st century, we'll be in this situation, well, in that situation. And that, of course, is harmful to us because once ozone starts going over middle latitudes, and especially the tropics, that's where we live, the solar radiation gets through the stratosphere then and is harmful to our health in many other ways. And this, I'm actually going to skip this one because I think I'm going a bit more slowly than I expected. So I'd now like to come to the carbon climate issue, and really, how can NASA contribute? And basically, I'm trying to build this on what we can do with observations, the types of observations we do, and also the historical precedents of what we've done on ozone. There's very strong observational evidence that the surface is warming. Of the last few years, they've, all years of this century basically are among the warmest 15 or 16 years in recorded history for globally average surface temperatures. So there's a very, very clear and undisputed signal that the Earth is warming. As Mr. Kerry said a couple of days ago, the role of greenhouse gases is well understood. I think something like 97% of scientists really believe that increases in greenhouse gases are the cause of the surface warming. Those things I'll illustrate with a couple of slides. We've been able to, using our existing satellite data, we've been able to estimate carbon exchange between atmosphere and land and atmosphere and ocean, just based on things like the vegetation distributions from MODIS that I showed you, knowledge about the water cycle and the precipitation, and lots of other pieces of information that we can get from satellite data. And we're able to use these in the diagnostic type of models that I mentioned earlier to really come up with good estimates of fluxes of carbon between land and atmosphere and ocean and atmosphere. We couple these with anthropogenic emissions inventories, the values reported by different countries, and also we include components related to biomass burning, so that's getting the CO2 from fires in there, and that's also estimated using satellite data. What observations we're getting now, and also what we can probably do with Earth system analyses. So basically, how can we work to the point where, just like ozone, we can project ozone now well into the future with a strong degree of certainty because we've used observational programs to help understand the chemical processes at work in the stratosphere and be able to use that in predictive models. And basically, the aim is to try to do the same thing in carbon-climate interaction models. So this is the surface temperature record as reported by GIS. And it's showing essentially, as we go from the early part of the 20th century, we have cooler anomalies, and as we go through time, basically this map turns yellower and redder. That's essentially saying the temperature in that one spot, if it's yellow or red, is warmer than typical. And you can see as time goes by, more and more of this map becomes red. And this is the observational evidence that we have that the surface of the Earth is warming. That's starting again. So you can see a buildup from blues, cooler than average over that long period, to warmer than average over that long period. And you do see regional differences. That's just the atmospheric circulation. A lot of plus minus differences happen. You just expect that. But overall, there's a redness appearing. The Earth is warming. This again is from my colleagues at GIS, and this is essentially showing that the observed temperature is basically compatible. Well, I shouldn't say it that way around. The model temperature is compatible with observations if we include the impacts of greenhouse gas increases, aerosol changes, changes in land use, and a couple of other minor factors. But basically, if you include only greenhouse gases, the temperature warms quicker than observed. If you include anything else, it stays around the zero mark, except for sulfate aerosols when it cools a little bit. And it's really the combination of greenhouse gases and sulfate aerosol loading, sort of modulating their effects somewhat, that gives you a good agreement between the model simulation and the observed global mean temperature time series. So there's this is one piece of the strong modeling modeling information that we have that tells us about the physical forcing mechanism of the temperature changes. This is a simulation of carbon dioxide in the atmosphere. It runs through just 1 year. And this is where I mentioned we've used all of the available information we have about land atmosphere and ocean atmosphere interactions to try to constrain the exchange of CO2 in this simulation. And basically, you're seeing the gradient between the northern hemisphere and the southern hemisphere. Essentially, the anthropogenic emissions are focused in the northern hemisphere. It takes time to get them to the southern hemisphere, so there's a gradient in CO2. Now, in the summertime, as the plants bloom, they pull the CO2 out of the atmosphere in the northern hemisphere and lead to a reduction. And you can see that, but at this time of year, you can see, again, the emissions from Asia, Europe, and Eastern North America, and LA in particular. On that side, it jumps out. Again, though, so the main emissions are happening in a few localized areas. They're getting into the atmosphere. They're transported around the hemisphere fairly fast, into the other hemisphere fairly slowly, and leading to the gradual buildup of CO2 that we see that's been measured at Mauna Loa. And the point of the 3D model there, this complex model, is essentially showing how those few sources emit and it gets carried around and mixed into the entire atmosphere. What NASA also has is an observation capability. It's building up this observing capability with the OCO2, the Orbiting Carbon Observatory, the second version. And this is showing observations from OCO2. What you see is that they're actually quite sparse. You were getting a few thousand measurements per day along those tracks that you can see. Even those few thousand measurements per day are way more than we have from any other observing system. We have about 100 or so in situ observing stations scattered over the Earth where we can measure carbon dioxide on just a few days. So this preceded by the GOSAT mission from Japan, and it will probably be in the future extended by OCO3 on the space station, and also a French mission called Microcarb has just been announced this week. So there's hope still that a lot of countries can work together and start building up more international types of collaborations. Here again is the OCO2 movie showing essentially it's getting signals where there's good sunlight for it to measure as we go through time. And one important thing is this is a column average of CO2 measurements. So it's not a measurement close to the surface where we'd really be able to infer the fluxes very directly. We're actually going to have to end up doing a lot of modeling to pull the fluxes out of this measurement. And here again showing the complexity of the system and the model as time goes by. This one's a simulation. It's a new simulation that's running over about 14 years, again using the observations to constrain the emissions, and in this case it's using a reanalysis where the winds are sort of a best possible estimate towards observations that we have. And it's showing you essentially that the model, this is a time series at Mauna Loa where there's a long time series of measurements, so that's the white curve, and the model is the yellow curve. You can see the annual cycle is a little out there, but essentially we're getting roughly the right annual cycle, but especially the increase over time of CO2 levels. And to compensate for that in the plots, the color scale is actually sliding with time. So the global mean subtracted, and you'll see the white bit of the color scale is moving along the color bar as CO2 mixing ratios increase from about 370 ppm in 2000 to about 395 ppm in 2013, I think this one ends. But again, so this shows us the growth and that we can reconcile this growth with a lot of observations that we have in this model simulation, and that we're able to see all of the seasonality of that. So certain hotspots of emissions, hotspots where things are taken out of the atmosphere. So using models again to bring everything that we know together, but only not with a predictive capability in this model for the surface fluxes. And we need that predictive capability to be implemented for climate model studies. I'm going to move on. So roles for NASA in carbon climate. Obviously, one of the strengths of NASA is our ability to develop new technologies for instruments, new types of observations. We've shown that. I mean, this past year, we've launched GPM, we've launched SMAP, we've got CATS on the space station, and there's a whole series of other missions in planning that use newer and newer technologies and are giving us better spatial information and also more information about different parts of the Earth system than we've ever been able to measure before. One of the things that we're able to do at NASA is what are called observation system simulation experiments. And that essentially means you simulate your entire observing system and then look at the impacts of adding a new type of observation to that. And with that, you can get very quantitative metrics using models of how a new observation might help us understand the process or contribute to our predictive or analytic capability. That's used very widely in weather modeling. For instance, the AOLAS instrument that's going to be launched by ESA quite shortly, there was a whole set of OSIs done to demonstrate the impact of that. We'd like to get us into the position of extending that technique to be able to do that for carbon climate modeling in the future. We have a whole bunch of forefront space missions. We're just reaching the end of the period of the first decadal survey. There'll be another one formulated over the next couple of years. And really, I think this is a great opportunity for us to start trying to get some of the carbon climate type instruments into the decadal survey and get funding for those in the longer term. I've tried to show, we're able to use the complex models to bring all of the processes together and really come up with analyses of the system, but from different types of satellites, combining different pieces of information of different parts of the Earth system and getting more out of them in a combined way than we are able to get from individual instruments by themselves. And really, longer term, the projections of the carbon cycle in the Earth system are a great goal. To do that, we have to get predictive components for all of the evolving features of the Earth system, and we have to make sure that we're using the observations as wisely as possible to be able to constrain those. And if we can do that, I think we'll be in a great position to influence not only the implementation of policies, but also the monitoring of carbon and its fluxes. Just as we've done for ozone in the past, I think NASA can play a great role in this for the nation and also for the international community, because there's, it's a global problem. There'll be a lot of collaboration in that. And so I believe that's my last slide, so we should be open for questions. And thank you.
Thank you, Dr. Paulson. Yeah, we have time for plenty of questions, so raise your hand and I'll come over to you. And we'll take two at a time.
Okay.
Hello, Alistair Graham, Humane Society International, Australia.
Okay.
One of our interests here in Paris is that countries find it fairly easy to measure deforestation, but they find it very difficult to measure degradation.
Yeah.
Is it possible to use some of these data sets to help countries make estimates with enough confidence to use them in their reporting?
Okay, and then the second question.
Bernard Tardieu from France. You have presented a lot of measurement for the CO2. Did you do the same for CH4, for methane?
Okay, good question. Yeah. I'll address the second question first. I think that there's great interest in the US in developing a methane measurement capability. I think methane, methane is even more complicated than CO2, I would say. There are so many different sources for methane, and its lifetime in the atmosphere is somewhat intermediate, and it's involved in chemistry. So it's a very, very, from almost every way you look at methane, it's a very complex molecule to deal with. It's obviously extremely potent radiatively for climate forcing, and it's extremely difficult to measure. So really, we're looking at LiDAR technology for measuring methane, so active things where we'll be shining a LiDAR from space and measuring how many photons come back. That's a sort of a mission in investigation right now. I think the aircraft, the LiDARs exist, they're being flown on aircraft, but they're obviously going to have to be validated, and then there'll be a whole lot of other work to do before a mission can be designed around them. And that will include the weight of the instrument, the cost of the instrument, and all of those other factors. So yes, we're looking at methane and hoping that we will be able to measure it. As for the deforestation and degradation, we do have Landsat shows very easily the deforestation when you repeat your measurements from year to year and see forests disappearing. Degradation, I'm actually not quite so sure whether we can tease that out of information from Landsat combined with the MODIS reflectance and looking at the changes, more subtle changes in the greenness of the land, of the vegetation over time. To be honest, I'm just not familiar if anyone has tried to do that, or whether they've succeeded or failed at that. So I can't fully answer your question. I'm sorry.
Any more questions? All right, we have two, one here and one there.
Hi, I'm Colin Westgard. I'm a high school student from Minnesota, and I noticed that a lot of the CO2 climate observations that you made were based primarily upon factors such as countries' reported emissions. As we go into the future with various, INDCs and promised CO2 reductions, are you going to be able to empirically measure their CO2 emissions, or are you going to have to rely on what they say they've emitted?
Yeah, okay. So, one question.
Jan Mattsson from Sweden. Are you able to measure emissions from, let's say, a city or from an area, such as this conference center?
Yeah, okay. I'm going to zoom back to the OCO2 measurements here. And I think that those two questions are actually quite similar, I think. Basically, what we can measure from space is at the moment, is the total column CO2. Now, that is equally sensitive to CO2 in the, say, in the 8-kilometer high range as it is to CO2 near the surface. So that makes it extremely difficult to infer that you're measuring at a point that's representative of the emissions from that place, because the emissions from here will be local when you measure, but the emissions from thousands of kilometers away can be transported up and across, and they affect that column. So a total column CO2 measurement by itself, it's very, very difficult to infer that any one particular city or country is emitting that CO2 from that measurement. Now, we do, part of this combined model data analysis is essentially using information about the vertical transport and the winds. We can start to understand how CO2 from any particular place gets lifted and transported in different directions. So, and that's a whole work by itself called inverse modeling. That's a fairly mature field, but it has been developed based on a very sparse data network of those few hundred surface observations. One of the things that we really need to do to make best use of these space-based data is to come up with better inverse modeling techniques, and we are working on them, that really use the information closer to the emission point than has been used before. The old methods use very, very long windows, and the transport error accumulates over time. So we're basically trying to get back to more like days to weeks rather than months to years in those assimilation studies. That being said, there are a few cases in the OCO2 data where you can see very, very hot regions, very, very high emission regions. And I think there's some work going on at the Jet Propulsion Laboratory where they're looking at emissions in the vicinity of LA, actually. And they're obviously based there. I think they've got some local interest. But there's a megacities project. They're looking at LA, Sao Paulo, and I think the third one is Paris, actually. And that's groups in different countries are collaborating to do that. And so there's some hope of combining these OCO2 measurements with other observations, probably in situ networks, like local ground-based observations, to try to tease out these fluxes on a more local basis than we can really measure them. But it's very typical. We're relying on inventories. We use those nightlight maps to spread those out. Basically, inventories are reported by a country. We're trying to deconvolve those into more regional, city and highway-based emissions where people actually drive and that. And other space-based observations help us to do that. The highway light, the lights are one of them, night lights. They show us where people live and where they tend to drive. Plus, a lot more detailed stuff about vegetation and everything like that.
All right, any more questions?
Hi, I'm Willie Schubert from Earth Journalism Network, and I was wondering how this type of information gets distributed to the public, and especially about the amount of computing resources. Maybe you can speak to the computing resources that go into something like this, and how the knowledge that you're creating is eventually reaching these policymakers and people.
So I'll go to this. This was a model run. It basically used 10,000 cores, and it ran for about 4 months using those 10,000 cores. So basically, our computing center got a new computer and we used it for a while before we opened it up to everyone else. This generated more than 4 petabytes of data, because it's not only CO2, I hasten to add, it's got aerosols in it, and also all of the meteorological information. We're actually using this simulation to synthesize an observing system for observing system simulation experiments. And that necessitated that we save data every half hour, and that's part of the reason why the data volume is so large, plus the fact that it's run on a mesh that's 7 kilometer squares over the entire globe. So it's a very fine resolution simulation as well. Now, those data are available to the public. They are available from our computing center for anyone who wishes to go and get them, to download them. We have like a file description document, and we have a 300-page validation document for this simulation that describes how good it is, and there are scientific papers being written. But I think that that's not really getting to the point where you would like us to go and sort of be able to describe more generally how useful it is. And I mean, part of the way we do that is actually this movie was created in our scientific visualization studios and at least distributed through them. And you know, this movie is also available to anyone who wishes to download it from the scientific visualization studio. There is a caption, and essentially we try as much as we can to give information that people can understand to use these for their own purposes. But you know, we could probably be doing I think we need to actually establish better communications with people to find out what is needed, how that is relevant, and you know, especially how to make it policy useful, because it's often the case that for policy, you know, we know what we can do, and policymakers may know what they want, and the gap between those two things is sometimes not easy to bridge, and it's a big challenge, you know, to understand each side and to provide the information in the most useful way to people. So that's something we're always working on improving, I would say. Thank you.
All right, got 2 more questions. Great.
First of all, an excellent presentation. Thank you very much.
Thank you.
The actual effect in the atmosphere is because of carbon dioxide and methane combined. Because of carbon dioxide and methane.
Yes,
but
that's
we are
right.
only talking about carbon dioxide.
Yeah.
So what is how do you say this is only because of CO2 and it is not a combined effect of CO2
right.
and CH4?
Yeah. Okay. So should I just answer this one question? Yeah. The climate model simulation I showed you actually had methane in it as well. So that effect was considered. I just didn't speak about it much today. And really, I think, yeah, we realize that methane is a very important source of atmospheric carbon and hence global warming as well. I've just focused today on CO2, and as I had mentioned in the answer to the previous question, yes, there's interest in NASA in developing technology to measure CH4 from space as well as CO2. So I wasn't attempting to say that methane wasn't important. I was just focused more on CO2 today. Thank you.
I think we have one question back here, and I want to remind everyone who's watching over the live stream that you can get your questions in using the hashtag AskUSCenter.
Thank you. Zoltán Sombogyi from Hungary. My question is, I think, very difficult. I'm addicted to these slides, very beautiful.
Thank you.
But I can't help asking, how about uncertainty? You demonstrated that these models might not be accurate with the ice sheet slide. How about the uncertainty of this simulation or any other, and how you suggest policymakers should take into account this uncertainty in the estimates?
Yeah. No, I think, you know, essentially this is an extremely important part of the big question. And uncertainty really gets at us, you know, on almost every time scale, space scale, and process scale that we can be looking at. And generally, the best way of dealing with uncertainty in long-term climate projections is to do fairly large ensembles where we make different assumptions and where we put, you know, if it's the uncertainty of a process, we try to give some wiggle room in how we represent that process to represent the scale of what we think the uncertainty is. And I think if we can do that fully, we'd be able to get a more realistic range of predictions. And that's also the same issue. If we know where to make those wiggles, we would actually be able to try to develop observing systems to try to pin down that uncertainty. And that's really why we need to use the models and the observations in tandem with each other to, as we go into the future, to really try to find where we're uncertain, try to pin it down. Uncertainty when it comes to, say, data assimilation for the, using all of the existing observations and combining them, we have statistical ways of trying to represent that inside the models. We put uncertainty on the observations, we put uncertainty on the models as well. And if we start, and we are starting to use more ensemble-based approaches, again, we can start to incorporate that uncertainty by having different estimates of the observational space, because we actually measure a radiance. We're using that to derive the physical quantity, so we can put more uncertainty on that. And for the models, we can start to include the lack of knowledge, lack of full knowledge about certain processes in them, and span the ensemble with uncertainty in that too. So I think we have ways of getting the uncertainty in. We are doing that to, we do that all the time with weather forecasts. If you look at ECMWF or at NOAA, NCEP, they're using ensembles of forecasts to come up with the weather forecast. And essentially, there'll be some outliers, and the skilled forecaster is going to be judging whether those outliers are actually giving good information or whether they're really, just because they don't fall into that box, they are not useful. And I think it's the same thing here. And uncertainty is really key to this, and representing it properly is a very, very important part of our job, I think.
Any more questions out there? If not, I have one. So we've been talking about satellites. Now, you can't wake up tomorrow and say, I want a satellite up in space, and build one in a month and put it up there. It takes years of time to plan it, years of time to figure it out. Can you get more into the international collaboration amongst different groups to actually put satellites up there to increase our Earth monitoring?
Yeah. I think that's a very good question as well. Obviously, satellites take years to plan and build, and right now, the U.S. has, NASA in the U.S. have launched OCO2. That's there. Before OCO2 was launched, the Japanese launched GOSAT, and there's been a great collaboration between the U.S. and the Japanese on that. The fact that GOSAT was there first meant that the U.S. could get very similar types of observations to what we're getting from OCO2, and that helped us improve the algorithms that we use to infer CO2 from the measurements themselves. So there's already a good collaboration there. I know as the Europeans start thinking of launching satellites, they've already been working with OCO2 and GOSAT data. So those collaborations really do exist at the scientific level, and I think they're evolving at the agency levels. We're always looking at what the agencies are doing in different countries. If we look at the meteorological satellites as an example of this, there's great collaboration. The Europeans have now the METOP series of satellites providing information that is distributed widely to the whole world. We use them, NOAA uses them in the operational weather forecast, just as the Europeans use NOAA's satellites. And even NASA's satellite, the ERS instrument on Aqua, is a very widely used hyperspectral infrared measurement. ERS was launched in 2004, I think, and that was the only hyperspectral infrared measurement up there at that time. Since then, we've got the EASI instruments on the METOP satellites by the Europeans, so their use of EASI was enhanced by having had ERS first, and now there's CRIS on the US satellites. So, I think there's a good back and forth. That's very well established in the meteorological community. I think it needs to be enhanced in the carbon and climate type communities, but I think there's already good contacts between the different countries.
Thank you for that. Any more final questions? We have one in the back.
Hi, my name is Jean-Louis from Canada. Maybe a difficult one. How did the science use all those data to create that target of 2 degree or 1.5? And what is the difference between 2 and 1.5? And I'm sure that the answer is not 0.5.
Yeah, I mean, sure. I mean, and that's a very hard question for me to answer, because all week I've been here and the negotiations have been happening in a different room. But obviously, as the Earth warms, there are more and more adverse consequences for every, even for every tenth of a degree globally. If the Earth warms a tenth of a degree globally, that means the Arctic is warming by 0.2 or 0.3 degrees. So with the Arctic amplification, so that means the more warming there is, the more ice is going to melt. So as the oceans get deeper, that means that every tenth of a degree is making some countries' coastlines more vulnerable to flooding. It's making Pacific islands more and more vulnerable to being totally uninhabitable. I think that there is obviously a difference between 1.5 and 2 degrees. But I think being able to quantify that, here right now is probably a little difficult. 2 degrees is better than no control at all, I would say. But the smaller the rise, the better.
Thank you. Any final questions? One more? All right. Can we give Dr. Stephen Pawson a big round of applause?
Thank you.
Thank you for the wonderful talk and those addictive images.